Yes, please.
It's okay. Can you see my screen?
Yeah.
Yeah, thank you. So sorry, this presentation will be in English. I guess I'm the exotic presentation today, even if Paris is maybe not so tropical. So yes, I'm going to discuss about this accident of the fire in at Notre de Paris. I want to speak about this at the modeler with a modeling point of view to see what data are available. Does this case can become a validation case? What are the few lessons we have learned and so on. So just very few words on the context. So the fire happened almost 2 years ago now in April 2019. It starts at the end of the working day, so everybody was start going back home and see what was happening going back home. So there is a large amount of wood located in the roof that has burned, but also a large amount of lead. So the dispersion that has been studied was the dispersion of lead particles. The fire has been during almost all the night, and it was fully stopped the morning after. What you can see on this picture is as the building is very large, the emission for modeler is a bit is a large source, can be a large source, and it's a bit complex. You see that there is a, I don't know if you see my pointer or not. Yes. The one of the main part that has burned is the roof here, but there is also this very thin part which is called the arrow that has been burned also, and then fall 2 hours after the beginning of the fire. So I will show you what the official modeling that have been conducted by the INERIS, which is a national institute in France. Then I will show what we have done on our side, some modeling. Look at the possibility to use this case as a validation case, and also some results of sensitivity test done with MET input. So about the official calculation done by the INERIS, the very first step is to estimate the source term. So that's not my field of expertise, but I can present to you shortly what the INERIS has done. You have a full detail in the report that is available online. So you have the link at the bottom of my presentation here. Roughly, the method is based on observation. So what we need to know is the burning rate of the wood typically to have the amount of gas that is emitted and the energy and the power. So this burning rate have been estimated based on observation and on this correlation, where you can see that the height of the flame is correlated to a spatial dimension and the burning rate. So a picture gives the height of the flame, and the spatial dimension is given by knowing the size of the church. So once you get that, it's for a specific time, and actually the fire is something that is having an evolution in time, and two phases are distinguished. The first one is when the fire is quite small, so there you see that there is only a small piece of wood that is burning. Then you have an evolution that is evolving with a square law. And then when you have a more complex, a large evolution of the fire, we talk of flashover, then what is important is not only the properties of the material, but also how the materials and how the piece of wood and so on are set together. So that's what we say into the configuration world. So you have a more complex, but still quite simple time evolution law. So at the end, it gives that kind of time series of the here it's a power, so it's in French, but it's power here, and you can simplify it in 3 phases, which is before the flashover, during the just after the flashover, and quite a long time after the flashover when the failure is quite constant. So the thing that Ineris gives the total power, the convective power, the total mass rate, and also some other characteristic of the source. So again, everything here is available, so anyone can use it. So in terms of modeling, then Ineris has just checked quite roughly at very local scale using the FDS model, which is a LES model. That's the power that I've estimated is in a good range. Checking that, running the model with this power, they get a plume rise that looks quite in good agreement with observation, but it's very qualitative and raw comparison, because the comparison was really done with this picture, which was taken from a plane. And then the more let's say advanced and used calculation was done in a larger scale. So the domain of modeling was 50 kilometers by 26 kilometers with a 100-meter resolution. So here you have the topography. So Paris is here, and it's quite flat in Paris, and in the west part of Paris, you don't have mountains for sure, but you have maybe 100 or 200 height hills. What is more interesting is that in this domain, you have very different kind of land use. So very dense urban area, but also more green part here. So very different roughness in terms of modeling. So the setup of the calculation, so it was done with PMSS, so Swift and Spray. In terms of emission, and especially on particular size, 3 scenario was used, because actually it is quite difficult to know the size of the particle. So the first scenario is quite medium size. Scenario 2 is large size particles, and scenario 3 is small size. And in terms of met input, they have used the result from the mesoscale model of the National Institute. And the results is given here. So what you see here is the position map. If you look in detail, you will see that it's not absolute, but only relative to maximum value, because Ineris estimate that there is too much uncertainties on the emission rate. So they prefer to show only relative deposition. But what we can learn from this is that in terms of particle size distribution, what is the most impacting is the one with the biggest, the coarse particle here. So this modeling has been used to also to do campaign measurements, so not done by the Ineris, but which is available by IRS. So what you can see here is a website, and everything is now open. Actually, during just after the incident and during the study, there is some quite politics, and everybody say that the information was hidden. So at the end, the institute was almost obliged to put everything in public domain, so you can get all these measurement points. So it's the position, it's not concentration, but all these points, measure points, are available. Um, so I don't know if INERIS or his other institute has done validation. We don't have done any validation because we don't have any commitment to do that, and we don't have any funding to do that. But for sure, it will be a very interesting exercise to check if the deposition are okay or not.
Maxime, 5 minutes.
Yep. So shortly, what we have done on our side, just at very small scale, we have run a CFD calculation. Data for the building are available on the website on the Open Data of Paris, so quite easy to build a 3D maquette of the SketchUp of the area. So here the cathedral is here. In terms of meteo, we have first used the meta of one of the airport of Paris, which give only ground values, and we have so extracted ERA5 vertical profile that give us value every 3 hours only. So we see that at 10 meters and 100 meters, the wind is blowing quite in a simple way with no shearing direction. So it's at least in terms of meteo, it's a simple case. We have used the source stem estimation of INERIS for sure. We have been located all the emission on the arrow, which was maybe quite made a mistake we have done. We'll see that after. And the solver is Code Saturn from EDF. So with ERA5, you get that kind of results. So it's quite similar to what INERIS has get with FDS. We get this shape with 2 branch in the plume, which can be explained by 2 vortexes that is appearing with a thermal effect. And in terms of validation, maybe yes, I will try to get shortly, but for the near field, there is many pictures that are available, and some of the pictures have metadata that are given its location, their time, their focal length, and we think that it could be a interesting way to do some validation. So you may know that focal length is used by people doing pictures, but actually for modeler, where we are using power view, for example, you have the very similar parameter, which is the angle of view. And actually, we discovered that you can change the angle of view in ParaView and change it just like if you're changing the focal length. So we have play on this with this idea with 2 pictures. So on this one, we have the time step, we have the focal length, and we try to then adjust our view in ParaView to get the similar view. And then we see that here it seems that our plume rise is a bit strong. Another picture taken from, we understood that it was taken from a tower here, the Jussieu Tower here, and the cathedral is here. And here the plume rise seems to be consistent, but on this picture the metadata were less available, so we have more uncertainties on how do we have to set ParaView to mimic at best this. And then very quickly on the met sensitivity. At very first, we have used meta, the ground data, and build an analytical extrapolation, but it was very different from what we get then from ERA5 or what has been used by INERIS with Météo France. So just to say that it's very, for that kind of plume that are going very high in the atmosphere, it's very important to have a good metadata also in the upper layer. So with ERA5 and AROM, the results are quite similar, but with yes, with a wrong vertical extrapolation, you have significant discrepancy on the plume rise. Yes, and that's it. So just to say that about the idea to use the picture database, maybe looking it in internet is complicated, but giving a professional photographer, we get more metadata, and we would like to have some time and funding to perform MSS calculation, especially used formulation for fire. Maybe it will be discussed in the next presentation. I don't know. Yeah, sorry, I'm a bit late.
No, it's